Are we recording?
All
right. So I was down at the Compose conference down in New York a couple of months ago, and ran around trying to gather speakers for the next few months here. I bumped into Austin and convinced him to come up and crash on my couch for
a couple days,
yeah, for a few days and give this talk. So all the way up from Texas now. So Austin was the GHC release manager for what, like two years?
And then Ben's doing a lot of the release management stuff now, thank God, because release management's boring. So, sorry.
Yeah, he's been buried doing consulting over at Well-Type, so I'll just hand over the floor and let Austin talk.
Appreciate it. How's it going? My name is Austin Seipp. As Ed said, a lot of you may know me. This talk is about improving our serialization library in Haskell, which is some work me and my coworker Duncan have been doing. Duncan's been working on it for quite a lot longer than I have, but I've been trying to actually get it finished up and released because it's quite nice. And this is what that talk will be about. So for a quick overview for people who aren't aware of me, I've been programming for a while now as a career. Actually, in my past life I did things like C++, file systems, security research, all that other nonsense. But today, as Ed said, I write Haskell for people all around the world, and many people know me as a janitor for GHC. So many people in this room have actually probably, talked to me quite a bit sometimes, mostly probably by reporting bugs. So this talk is not, whenever I sort of set out to do this, I didn't really want a case study in like optimizing a library. I more wanted to just sort of go over the general points of our design for this new successor to binary. There'll be a bit of code diving, some examples, stuff like that, but for the most part I wouldn't really, perceive it as, you'll walk away from this knowing how to write really fast Haskell, but it'll give you tips on some of the design space. So speaking of that, today everyone we know uses a package called binary. And if you have really written almost any non-trivial amount of Haskell code, you're probably using it directly or indirectly. So binary, as the name says, is sort of this package that we use to serialize and deserialize values, right? And that's a pretty broad spectrum of things. But binary does it all. We use it for talking to other systems by doing arbitrary parsing or serialization. So for example, if you needed to parse something like a TCP header, right, you could use binary for this. If you needed to serialize a TCP header, you could use binary for this. But also we don't just use it for arbitrary things, we also use it for Haskell values, right? I have a cache somewhere, I need to store some data structure in it, a string, a list, map, whatever. I need to be able to take that Haskell value, put it in a byte string, and then send it somewhere, right? Today, binary-serialize-cbor, which is our successor to binary, only deals with these last two things, right? So we're only really going to be talking about actually parsing and encoding Haskell values. Inevitably, we do plan on this library taking over these two as well, but that will require a bit more design, and this is where the main focus of our work has been. My computer is taking off like a jet. So let's start off with the review of binary, right? Binary has sort of these two types that we use all the time, which are called put and get. Put looks like this, right? So we have, if you look at it, right, there's this sort of special pair. It's not really a pair you normally see because it's strict in the second argument, for the second component, but it's lazy in the first. And then we have put m, which is just a wrapper around this pair. And then there's another alias here for the simple case where you don't need to return any values. So this is a writer monad. It's a writer monad over builder, where builder is the internal monoid. And if you sort of fill in the types, you can see this. Builder supports really efficient concatenation. So it's very efficient, unlike a lot of other data structures we have, to just slam things on at the end over and over and over and over again rapidly. And Builder has a lot of other nice things, like if you know sort of the size of what you're going to inevitably be dealing with, then you can pre-allocate it so you don't have to like double the space or anything. But that's fundamentally really all it is. It's just a specialized writer, right? And get is sort of this much more confusing sort of state monad. And this actually is a state monad that's been sort of unrolled. I believe this is actually I think this is like code density of state or something, right?
It's, no, actually, it's just because the byte string and success, I think, are not tuple.
Oh, okay, yeah. So, so it's unrolled here, right? And this interface is kind of weird because when you get something, right, you have a byte string that you're reading from, right, whatever, maybe a TCP packet you got, and then you have this sort of function, which is another continuation you call on success, right? So if you have a successful parse of something.
Oh, the CPS, it is CPS.
Yeah, yeah. And then finally, you know, this is giving you back a decoder type. And then the actual success type, as you can see here, is a continuation, just another function. It's pretty, like in all honesty, it's kind of confusing to look at this. Like even today, whenever I look at binary, like it's, you know, this sort of interface is a bit, you know, kind of weird.
If the byte string was the second argument, and the success had the A as the first argument, then you'd have a good instance.
Oh, okay, yeah. But yeah, it's a bit of a weird interface, and it's kind of unwieldy because we've got like all these continuations hanging around. So it's actually kind of like a bug-prone interface. It's kind of easy to shoot yourself in the foot if you write incorrect code sometimes, but it works, and it's what we've been using for, you know, the past decade or so. So yes, as I said, put is sort of a monoid over builder, right? And whenever you want to put something, it looks pretty much like this. So many of us are familiar with tell from writer, right, which sort of appends onto the monoidal state, or, you know, does whatever the composition operator specifies. And then, you know, if you have that, well, I mean, you know, if you're putting a word and you just turn it in whatever you gave into a byte string, and then you just append it, you just slam it on the end. That's all you got to do. And put is very simple, actually. There's lots of functions that look just like this. They're basically just tell, and then this part is just, you know, make byte string out of the argument. Pretty simple. Yeah, and as I said, Git is sort of this unrolled continuation interface that, you know, gets sort of unwieldy to implement if, you know, you either don't have a high tolerance for pain, or, you know, maybe that's the only reason you'd implement it. And Git and Git and put are like okay, but they have some problems, and Git especially has a lot of problems. So one of them is that these interfaces lead to a lot of code, right? Think about whenever you have a binary value, right? We just saw this whole continuation interface up here, right? So if you have things that are parsing, right, then you've got a bunch of continuations you need to stitch together, right? And you need to be able to take care of all the error cases and all this other kind of stuff. When we write these functions, when we write things to use get to parse, right, they look very simple, right? Like, but whenever, oh, I should say decode. I'm sorry, I slipped in the wrong example there. But it's essentially the same. Whenever you use these functions, right, because they're just wrapping continuations, you end up piecing together lots of them, right? You get this huge ball of code that's like, you know, very long-winded. And it's not really, like, I tried to like get a good example, but it gets pretty dense when you look at the core output, even if you like make it all pretty and stuff. So it leads to a lot of code. And then with all these continuations inside, right, you're allocating byte strings all over the place. You know, you have failure cases where you're branching all over the place. And this is sort of exacerbated because in Haskell, we tend to inline things a lot, right? So you're telling the compiler, for all these sorts of instances you write, you're saying, hey, anytime you see this, just inline the definition. Just try as hard as you can. And that ends up building up a lot of code. And even more than that, these interfaces use a particular construction in GHC called rules, which sort of allow you to specify rewrites. They allow you to say things like, if you see a function applied to some specialized type, then you can call a faster version. But rewrite rules are even add to the fragility, because it's possible where, you know, you'll stitch together all these pieces of code, and then you would expect some rules to fire, and they don't. And then everything sort of, you know, tanks from there. You just get terrible performance. It's sort of intrinsic to this design. And like I said, if you sort of just, you know, mentally unroll all that stuff, right, you can sort of see like how this all ends up adding together. And typically, you know, I mean, binary is like, you know, decently fast, but there's quite a bit more we can do here. And like I said, because you've got so many continuations, you've got so many functions you're allocating and passing around and byte strings, you know, it hurts your performance too, just independent of any optimizing things, because you've got more garbage to collect, right? You just actively have more live data. So, and another problem with binary too, aside from the fact it's very bloated, is that binary doesn't exist separate from Haskell. So if I have a serialized value somewhere, and someone wrote a function to serialize it, I have no clue what that value means without the original source code. There's no structure, there's no schema to the actual underlying, bytes, which kind of makes sense, right? You're parsing or serializing arbitrary things, so I mean, it would kind of make sense. But if you're serializing Haskell values, right, it's pretty annoying and tedious that you actually have to have the instance on hand to do anything with it. You can't even examine the structure or traverse it without anything, without the source code available, which is fairly annoying, actually, in practice. So my boss, Duncan, like sort of identified a lot of these things probably about 2 years ago, I think, when he started working on this. And you know, we played around with a lot. He played around a lot with a bunch of different sources, but you know, we kept coming back to these things about where we're generating lots of code, where you know, we don't actually have a schema or anything, and you know, we need better than that. For an example, we have lots of clients who have problems with binary because they end up where they have large memory spikes. They have large garbage collection pauses, right? So it's pretty important if we can actually improve on this substantially. So the key idea behind this library is we write the optimal code. We don't try to generate code. We don't try to do any sort of fancy sort of stitching together of a lot of functions or anything like that. We write the actual very low level, you know, very bit blasting code that you know, most people in Haskell don't want to write. So the underlying format that we use to address this sort of schema thing is a format called CBOR. CBOR stands for the Concise Binary Object Representation, and it is actually an RFC. I did no idea this existed until I started working on this library. And you can think of it kind of like a structured form of JSON. So like if you have any arbitrary CBOR value, you can always just parse that into a data structure, and you can always walk over it, traverse it, do things like that. And CBOR is actually pretty nice. You know, JSON is fairly limited, but in CBOR we have lists, we have maps, we have floats, integers, strings, all these kind of things. It's actually, you know, fairly rich from a user perspective for like this sort of really low-level binary format. And when I say they have maps, I mean maps are actually a strict part of the actual AST, the description of the format. So it's actually fairly nice. So you can do things like encode. It even has support for things like you know, maps that are fixed size or maps that are unbounded in size and all kinds of other things. So it's actually a pretty rich format. It's actually pretty nice. I mean, you have to do obviously binary parsing, but you know, that's sort of the name of the game. And there's something that binary-serialize-cbor does that's very, very important. It's probably perhaps the key component that makes this library good. So whenever I was talking earlier about, you know, you have sort of these functions that encode or decode things and you're stitching them together, well, you're sort of giving a description of a data type, right? And then the compiler immediately produces code from that. It immediately produces this big ball of code that will parse that, right? This is what we call in Haskell a shallow embedding. For a simpler example, let's say I had a DSL and I was compiling it to C, and I have the term A plus B, right? One thing I can do is I can immediately just transliterate that into a string. I can have the output string A plus B, right? That's a shallow embedding because I'm going directly from the encoding we have right out to the source. There's no intermediate form. And that's what binary does, right? So you stitch all these little pieces together, and then once they're stitched together, right, you just have a ball of code that you can run. CBOR uses a deep embedding, which, you know, for a performance thing is kind of weird. And a deep embedding is instead where we build an abstract syntax tree, right? So the first thing we do whenever you want to serialize or deserialize something is we actually build a tree, a syntactic structure of what the thing we're expecting to parse or serialize is. And then we interpret that AST, right? So we actually have an interpreter that runs over it and does all the things. Kind of weird, because you would think, you know, if you want to actually go faster than the competition, then it wouldn't make sense to sort of have this intermediate value, right? You'd think going straight from code to code would be better, rather than like parsing and interpreting something. But it turns out to be anywhere from 5 to 7 times faster in practice. And there's
build the AST.
To do actual parsing. To do actual parsing or serialization, despite the fact there's this AST in play.
You're making a claim about your implementation, not about shallow and deep embeddings in
Yes,
the
this is a claim of our.
And in particular, binary is deep or shallow embedding versus binary serialized CBOR.
Because you're not fighting with all the rewrite rules and hoping that every serialized instance written over your entire program is optimized together into one giant ball of mud.
No, yeah,
and
good
you're
question.
Not fighting with the code size of that. You just have the size of the one little interpreter that walks over 80.
And as awesome as that is, and it's great, you also have 10 years of experience and reflection on
Yes.
on the last way they made it as fast as they
And
could.
actually, you know, we weren't the ones who thought this up. One of the people who worked on binary, who wrote Builder actually, Simon Meyer, he had actually investigated the same problem like over 5 years ago, and he said he was actually the one who first proposed this idea to Duncan was rather than actually, you know, generating flat code immediately from, you know, the structure of the type, then what if we actually built a syntax tree and we tried to optimize over that, right? And like I said, sort of that's the difference, right? We want to write optimal code. We don't want to write an optimal code generator. Writing an optimal code generator is very difficult in practice. But if we just write fast code ourselves, right, then that's actually quite a bit easier in a lot of ways. Obviously, not everyone's going to hack on sort of this optimal code, but it scales well from small examples all the way up to big ones. But it's sort of like counterintuitive. You know, you build this structure, and then, you know, you interpret over it, and you would think that's slower than just writing out the values into a buffer directly. But in practice, the library is actually about anywhere from 2 to 7 times faster on average. So it has a very, very simple API. There's a simple class called serialize, and has 2 methods, encode and decode. Unlike binary, encoding is monoidal, and decoder is monadic. And I believe, if I remember correctly, in binary, encode is also monadic.
It's a monad that just happens to randomly uselessly pass around the unit.
Yeah.
We'll hope that the optimizer gets rid of.
Yeah.
Okay. Encode is monoidal. Okay.
Yes. And I'll show an example here in a second.
That makes sense.
So here's how it represents these kind of things. So there's kind of a lot here, but we can step through it. I meant to put that on your slide. So you got the first thing, which is your encoding, right? That's the thing we need to return. And sort of this weird type that wraps a function from a token to a token. And if you actually look around in the base library, this is actually a more specific instance of a monoid. It's actually called monoid endo tokens. Endo of A takes A to A, right? So that's just a wrapper around, you know, any A to A. And then it has the exact same monoid instance and everything. It's just a more specialized version for this particular type. And then we have the tokens type, which has a whole bunch of different cases, but just as an example. We have positive words here, for example, which is one of the cases that we can encode a value, or encode in a 64-bit word. We actually have the word that we're going to encode, and then we have tokens. We have the sort of rest of what we are going to do, right? So whenever if you walk over, you know, a TK word here, then you have the word that you want to do encode, and then you have the rest of what you had to do, right? So it's sort of wrapped up in this kind of odd interface, but it's really not much more than a list, right? It's really just a list of all these tokens that you want to perform in order. And then you have like simple encoders here, right? So like if you wanted to take a word and make an encoding out of it, just wrap it in, you know, a token word, and then wrap that token to token function in encoding, and you're done. So all of the encoders in binary-serialize-cbor look exactly like this. They take whatever arguments they expect, and then they just wrap it in encoding, and that's it, right? And decoders use a kind of similar interface. They actually have like a continuation inside, but fundamentally it's essentially the exact same thing. And so you use a monoidal interface to build these encoders, right? So if I had a foo as an int, a float, and some map inside, then I actually use imappend, or, you know, the diamond operator, to encode, encode, and encode, right? And because it's an AST, it's not some like opaque function. It's not some continuation. If this type was exposed, you could just walk over it, it'd be fine. And because of this, right, think about what we were saying earlier, right? We have some sort of encoding, right? And we would normally stitch all these functions together. Here, I've got like 3 data constructors, right? Like there's nothing there. That code is not big at all. Like the actual compiled form of this is tiny, right? And that's actually a problem with binary, is actually it can create a lot of bloated code even if the code is fast because it's generating so much of it. And this is, on the other hand, is just tiny, right? It actually has quite a big effect on end user interfaces. Like if you actually look at this sort of size of the programs that the compiler emits, it actually has quite a big impact. Oh, I forgot to flip out that slide. Oh dear. So I didn't quite get all of my slides done because I sort of got lost in Boston earlier today. So maybe I should just go ahead and start doing the diving, right? So let's go ahead and just start looking. that the right? Where was it? Ah, there we go. Can everyone see that? Is the color highlighting on the terminal, I hope, isn't too bad. Okay, so let's see here. So let's look at that encoding interface first, right? So there's a whole bunch of different encoders we have, right? Each one from a function or from an argument to the output encoding type. And like I said, all of these look exactly as you'd expect, right? Like let's go down, right? All follow the exact same pattern. There's really nothing special going on in almost any of them. You can encode null values. There's some other things that I didn't quite touch on. But one of the nice things about this, right, is that if we have an abstract syntax tree describing the thing we're going to serialize or deserialize, then we can interpret it. We could, write out CBOR. We could write out a description of the CBOR. We could write out a simpler backend that didn't use a complex binary format, perhaps one that was textual to make it easier to read. So we actually do have that. There is a module in here, for an example, of the modularity we get called flat term. And flat term has these functions. Oops, wrong terminal, I'm sorry. So we'll look at flat term for an example. So flat term is sort of this. Flat term is just a list of these things called term tokens, right? And term tokens are basically the exact same encoding tokens we saw before, but they're not monoidal, right? This is just actually a list. So a token of an int just takes an int. A token for an integer, an arbitrary size int, just takes an integer, right? And then we just have a list of those. So this is actually one of the nice things about this library, because this interface also exports a function that takes an encoding to a flat term. And then it has a function that takes a decoder in a flat term, and it gives you back the original value. And this is actually really, really useful because you can encode invariants in the underlying data type here. So one of them, for example, is that in CBOR, if you have like a set of values, right? If I had like 3 integers, that has to be in a list. You can't just have 3 integers side by side in the result, right? That would not actually give you valid CBOR. So this actual flat term interface actually embodies that. So if you were to actually just serialize 3 bytes next to each other and not put them in a list, you actually wouldn't be able to decode properly. It would throw an error. But these decoders are like very simple for the most part. There's sort of some special cases to handle large integers. But whenever you convert these terms, right, I mean, you convert from, token bytes with this BS and these tokens, just, create token bytes and then keep converting. Just iterate over the rest, right? And then you just get a list back. So it's essentially just a slightly simpler form of the input type. And then you actually have from flat term, and from flat term sort of guarantees these invariants. And it has a whole bunch more cases for all these like integers and stuff it's dealing with. But it's really not that complicated. And you can see sort of the continuations happening here. So whenever you have like a consume int with this token, right, then we're going to parse over the continuation of that int. We're going to unbox it and continue. And for the most part, this is actually really nice. So what we do, for example, is we export these for users. And then you can write quick check properties over them. You can say, I have a data type, and I want to make sure that every encoding of it is valid. You don't actually have to go all the way to CBOR. You can just completely use this very simple backend, which is convenient because you can find bugs so easily with it. It's very easy to understand and unwind this code. And that's an advantage you can only get by actually having a separation of concerns, where you have a syntax tree, and then you have whatever backend you want on top of it. It has proven very useful for finding bugs in a lot of instances we've written for things like clients who have been using this library. Even our own instances has actually been pretty useful. And aside from that, we can actually write and read them into this format. And this is where sort of the low-level magic comes in. But it's wrapped up in a nice interface. So we've got something that takes an encoding to a builder, encoding to a lazy or a strict byte string as convenience. And what they do, right, is they just sort of step over the encoding you give it, and they just kind of push stuff into a buffer, right? So you've got a buffer that you've allocated, and then as you're walking over every piece of the encoding, right, you just write that into that part of the buffer. This actually is kind of interesting because, you know, before put sort of had more of this thing where it had like a builder that it was appending to, and here encoding is what really has the, you know, sort of builder that we're appending to. And BI and PI actually are, yes, they actually are the builders for byte string. So, but I mean, that, you know, it seems, you know, relatively simple, right? You know, for every singular token we go over, and we just sort of write out that value, and then we keep going. We iterate to the next one. And one of the nice things about this is that because we're the ones writing this, this particular this is all, you know, fairly simple or whatever, but because we're the ones who are writing the optimal code, we can take all sorts of little hacks, you know, quick fast paths, all kinds of stuff that we can actually use that you wouldn't be able to do if you had to generate the code and handle all these cases. So as an example of that, you know, if you know the size of some list or map or whatever that, you know, you're trying to encode or parse, right, then it's very easy if you have that, you know, to just create an exact fixed size buffer and then just write all that in and you're done. And you don't ever have to reallocate or move or anything like that. So you can, so whenever you have this separation of concerns, when you are the one writing the optimal code, you have tons of room to play around with all kinds of, you know, optimization tricks. And that is what really pays off here. Because, again, we're not having to generate optimal code, we get to write the optimal code. And for, you know, a pretty narrow specific domain that's actually not infeasible. And then, you know, aside from this, like, I mean, this is really the bulk of actually writing out CBOR values. And then the rest sort of stuff is, you know, all this making sure that, you know, words are encoded in the right format with the right bit set so you can, you know, make sure that you can parse them right and stuff. The rest of this is really just specifics of the underlying format. Like small integers have a different encoding than big ones, stuff like that. But otherwise, I mean, you know, fairly simple. Like, I mean, you know, because most of it is just encapsulated right here. You know, you just allocate a buffer and then you just walk over and just put stuff into it. And particularly for reading, this is where we take a big advantage of this. And read is really the monster here. Read, I think, is like, yeah, it's like 1,600 lines. And that's because whenever you're reading things, we sort of do a lot of these tricks where you have things like a fast path and a slow path, where you know in advance that, you know, you have some structure you're dealing with, so you can say, all right, I'm going to read that, and then I'm just going to go ahead and skip ahead. Or you may not need to read something, so you can just skip it entirely. So we have sort of all these cases where, you know, you have a fast path, and then if some invariant is broken, then where's slow path? Go slow, right? So you run the fast path, and then you look at where it finished, and then, you know, we actually internally sort of keep track of chunks of the input. And if you sort of end on this boundary of the input, then, you know, you fall back because you can't easily parse, like, you know, some fixed size buffer. So that's actually, again, another advantage we have because we're playing these tricks inside of the interpreter, right? This is all, you know, completely fair game for us. And another thing is that doing this allows you to exploit underlying aspects of the format, right? Like if I was just to write out 2 bits, right, there's not really much you can do if I was just to write 2 bits. I can't do anything more than just put the 2 bits next to each other. But if I'm encoding something into CBOR, then I know for a fact what the underlying structure is going to look like. So for example, maybe for, you know, 2 values, you can just have a very fast path that always just, you know, has exactly 2 values and it can just, you know, do the most efficient thing possible. It could be written in assembly or something, you know, as far as you want to go.
Sorry, when you're building this this AST, is that for the data type? Is that once per data type, or is that for every value you encode, you build a tree and then write it out?
For every value you encode,
okay.
Right? Because let me see if I can go back to the. Right. So every time you encode a value, right, you get an encoding back. That's an AST, okay. Right? So you're calling. So every time you need some encoding of some value, then you're always building a syntax tree out of it.
Is there some reason? And I know it's hard to do. So but is there a reason that sort of building a tree for a data type and then, say, running over it, composing a bunch of functions, and here's your encoder decoder functions? Was there any reason that wouldn't work?
If I understand what you're saying, I don't think so. I don't think there would be any reason it wouldn't work.
I think the main thing was that doing that was really brittle.
Yeah.
Like you wound up with a huge
So that's
pile,
what
huge
binary
pile of
does.
code
Okay.
that was the mixed encoder traverser.
Okay.
Yeah. Here, yeah, you know, sort of here we're separating the actual, you know, encoder from the actual aspect of writing it. So, you know, we want encoder to be, you know, fairly simple and like straightforward and, you know, not much more complicated than it needs to be.
Like all that builder code is like ridiculously inline heavy and stuff like that. It's sitting there doing everything it can to try and scribble into byte strings
Yeah.
with zero overhead or as close as it can get.
Yeah, but then it turns out, you know, whenever you actually get into larger sample sizes, it turns out it actually can tank pretty hard.
But
Because
microbenchmarks really well.
sort of, you know, random things like, you know, if you're wearing a green shirt on Friday, you know, or whatever, it may randomly get slower because you actually, you know, tweaked one character somewhere.
I'll talk afterwards.
Yeah. Oops. And so, you know, that's kind of the idea behind the reader as well, right? And again, this sort of high-level format we have really allows us to take advantage of what we're parsing, which we have actual structural information about, and then what we're actually serializing, right? The values we're giving out. And this is a huge advantage as to why it's so much faster than the competition. So one thing, you know, we've been thinking about is, would this trick also work for arbitrary data, right? And me and Duncan aren't entirely sure, but we think it would probably be a win. Like, you may not get like 5 times faster than binary, like, you know, if you're serializing, you know, arbitrary values, but you could probably do about 2 times as fast. Again, because whenever you're dealing with, you know, arbitrary data formats, there's no underlying information that you can exploit as the author of this code, right? You just have to do whatever the user told you to do. Parse 1 bit, you know, read 1 little Indian integer. There's not really much room for being able to play tricks to parse things faster. It would probably still be an advantage purely because, you know, you're not doing all of this, you know, sort of horrible inlining and, you know, all this garbage collection's happening because you're allocating so many things constantly. But it would probably be a win, but it probably is not as big of a win as for this. And eventually we will experiment with that, but we haven't today. But the fact that we're using CBOR and we're exploiting underlying aspects of the format is critical to sort of the things we can do. And it's critical to the sort of things we want to do in the future for it. So let me see here.
Are there other tools already that, you know, consume and produce CBOR?
Yes, actually there is a...
Transparency, you know, amongst applications. Can you use CBOR for the same thing?
Yeah, CBOR actually is supported. I'm trying to find where my browser is. I might close it. CBOR actually is supported by other tools and libraries. So one of the nice things is that you can, you know, you can take that CBOR value and, you know, throw it into a whole bunch of other tools, or you can parse arbitrary CBOR. It's not exactly the most popular format, and I wanted to show sort of, there's an online tool called cbor.me where you can actually get like a really nice encoding and decoding of, like, you know, what the input might look like, a list of, you know, 3 integers, and then what the output actual binary is, and it's like nice and structured and stuff. And it is nice for interop because one module I was going to show, oh, there it went, and I lost it again. One module we have actually allows you interop with arbitrary CBOR. And it's actually interesting because of the way it's built. So let's say you didn't have a Haskell value serialized. Let's say some Java program gave you a CBOR value, right, and you wanted to parse that. Well, it's actually pretty easy with our library. So the first thing we do is we take that you know, BNF, that abstract syntax tree, like from the RFC that describes, you know, what form the CBOR value can be, and then we literally write that as a term. So this is actually a Haskell version of basically the CBOR description of the RFC, right? You have ints, you have arbitrary size integers, bytes. I think bytes I is, you know, potentially indefinite string, like if you know, you can encode something like the string A forever. String I, lists, maps. You can give arbitrary tags just as metadata. There's bools, there's nulls. This is literally an exact copy of what you would see if you went and looked up the RFC.
So when you talk about being able to parse arbitrary things, you mean things that are other than what's shown there?
Yes, things that were not serialized by Haskell. CBOR values that were not serialized by Haskell, I'm sorry. Arbitrary CBOR, not arbitrary, just any arbitrary value. And so if we have that term, and we have two functions, right? It's actually kind of nice, right? Like if we wanted to encode that data structure into an actual term, then it's literally just a transliteration, right? Like every single one of these is extremely obvious, right? Any given int, you just give an int back. Any given integer, you encode an int. And then the interesting thing is the decoder. Because one of the nice things about this interface is that you can peek. You can look at what you're currently about to deal with. So we can decode any arbitrary term because all we have to do is peek at what we're looking at, parse that one thing, and keep going. So let's say you gave me some arbitrary term. Well, if I got an integer back, then decode that, and then give me the word. If you had some where's the list interface? Right. So if you had some list, right, you decode the length of the list. Right, and then you keep going. You flip and then you keep going so you can recurse into the list and begin parsing everything in there. And so you can actually parse arbitrary values. It's kind of interesting because this is actually more like an alternate front end. Like if you wanted, you could use this entire library just through this data type, and that would be fine. And there actually may be cases where you want to do that. As an example, if you had some Haskell value that had an instance that you wrote, but then you needed a slightly different form for interop, this would be an easy way to do it. You can just build this and serialize it into any valid CBOR term. It doesn't have to be related to any Haskell data type or any other data type in the world. It can just be arbitrary. So it's kind of interesting because this is almost like an alternative front end to the library. Like you'd never even have to use this if you didn't want to. You could just always use this. And there would be, maybe a little bit of overhead, but fundamentally it's, just an exact mirror of the things you're going to write out to the disk. So that's actually kind of nice. We actually can on top of the fact that we can have multiple backends, we can actually fit an entirely new front end onto it that looks exactly like the actual CBOR representation. It's actually quite convenient. And you may use this, oh, go ahead.
Super nitpicky. Your tag type seems like it seems like you're skipping the case where you have a tag and then a tag and then a term.
I'm not sure what you mean. Sorry.
You can have they specify that if you have like a tag A on the next thing, which is tag B followed by a string, and that's A applied to B applied to the string, not so you can have two tags,
right,
one after the other in the stream legitimately, and the type seems to not say that because it doesn't have any interpretation on the tag.
Yeah, no,
but who would do that?
Well, right here, right, if you have a tag, right, you encode that tag and then you encode the term that it has inside it, right? So you could have just another tag.
Oh, okay, yeah, okay, that's fine.
I was sitting
Yeah,
there,
no, you're right, you're right.
Wait, there's a term right there.
I was expecting them all to end up getting compressed in the exact way that it says that they're not, because I'm an idiot.
Oh, okay. No, don't worry about it. I was sitting there, I was like, wait.
It's almost a problem.
Yeah. But yeah, it's kind of like, nice that we have sort of this much flexibility sort of with the underlying storage type. And this is something that you just can't do in binary, right? None of these analogs even conceptually exist in that library. There's no concept of actually having, like I said, a schema of what you're dealing with. And this is actually really useful too. So we have clients that are using this, for example. With a tool like this, you can write migrations, right? So one of our clients has a case where they're processing terabytes of data with Haskell, right? And you don't want to just throw away 10 terabytes of data that took 3 hours to make because you adjusted a schema slightly. The library doesn't help with this right now, but using something like this, you can absolutely write your own migration strategies, which is extremely convenient. For people who have used binary today, you have to use something like Seipp copy for this. And we would eventually like this library, we have some basic design ideas, but we would eventually like this library to provide help for versioning and migration. And that's one of the nice things about having such a rich underlying structure. So you can do things like, if you add a field to a data type, right, it should be very easy to migrate that to have a default value that you would deal with if you read in data. And then you can do sort of other clever tricks, right? Like if you serialize something, and then there's a new version of it where you remove a field, right? If you know that, if you have this CBOR term, you can actually just skip over that. So while you're parsing, you say I don't have, there's another field here that I should be parsing, but I know that I don't have anything, then just skip over it, done. You don't even have to error out or anything. So there's lots of actual tricks you can pull when you have this much information, which is critical. And the versioning and migration strategy is one of the most important, I think, because it's one that happens quite a lot. and safe copy is sort of annoying to use. I mean, it's kind of got a nice API, but it fundamentally suffers from the same restrictions as binary because you always have to have the source code available. You always have to know the exact type to have any sort of information about the underlying thing at all. So it's really more of a a solution to the problem, but it's not really optimal. And right now we don't have any sort of versioning stuff, so you'd have to use these tools specifically like by yourself. But it's not. But given the performance, not a bad idea. Maybe something to live with. And then, okay, so I'm gonna just rant for a second. If you write Haskell libraries, please, for the love of God, write documentation. Like, it is insane, like, how often I see libraries that are completely sensible and have 0 examples. Like, it just doesn't make sense. So, like, as an example, for this library, I have a whole tutorial module. And we've been working on sort of the interface and stuff, so I haven't fully written it yet. But this is not being released anywhere until this is written. Please, just write a tutorial. It doesn't really matter how obvious or like, nicely abstracted the types are. Just write a tutorial. Like, it makes me sad. You know what I mean? It's the meme of, types have a lot of information is true and false at the same time.
Amen.
Yeah, it's like, you tell someone that and, it's like, you might as well, just be saying alien words for most people, right? And like beginners especially aren't going to have a lot of intuition about the way types unify or they fit together. Most beginners don't even get the idea that you can flip 2 arguments and that function is technically the same, right? So you can do kinds of all sorts of things that where the types line up, but beginners have no intuition for this. Hell, I have a bad intuition for it. Sort of whenever you play type level jigsaw, I mean, even I sit there and just like sort of, play until the pieces fit together. And it literally could have been solved if someone had spent 10 minutes to like write 3 examples. You know what I mean? Like it's just completely frustrating. So, just as a side rant, yeah.
Preach, brother.
Yeah, please write documentation. In all honesty, I would just encourage everyone to write tutorial modules like this. This is an idea I got from Gabriel Gonzalez, or as many of you maybe know him, Tecmo. And I think he is completely right here. And for a library like this, it's even more important, right? Because there's actually, aspects of the underlying format you may want to be aware of. There are use cases you might want to be aware of. Oh no, hope my computer doesn't die. And so yes, please, yeah, can you grab that out of the wall? So yeah, please write documentation. I think everything in this library is documented now except for the tutorial. But like I said, because we're sort of still playing with the API, oh no, the decoders don't have a tutorial yet, or any docs. Term I think has, Term has like a nice little spiel about everything. Encoding and decoding do as well, I think, and they even go into some of the details. Yeah, just write it. It's tedious and it sucks, but I mean, just do it. Like no reason. Oh man. So I spelled serialization with a Z here. Duncan's going to be mad at me. I actually wonder, hold on, wait. Oh, shit. Yeah, it's bad. Jesus. Okay, so patch is welcome for that. The funny thing is we deal with this in GHC all the time. I think we actually have the Americanized and British versions of like specialized, because Simon always writes it with an S, Duncan writes it with an S, I always write with a Z, sort of, yeah. There should be like an actual, recommended way of spelling serialize for Haskell maybe.
Or you could just make both work.
Yeah. Man, that makes me sad though. I'm like actually way more sad about that than I should be. And then, so as another example, like let's look at some little programs using this. So here's one that's very simple. This is actually just dump arbitrary CBOR file, right? Pretty easy. Take the extension, read it, deserialize from bytes, and print it. And this is decoding it with that term module we saw earlier. I'll show an example in a sec. And then here's another one that's probably more interesting to a lot of people, ASON. You can pretty much take any arbitrary ASON value and just write it right into CBOR. So here is actually a decoder for ASON values. And then, where's the encoder? Oh, there's the encoder. So encoding is very simple. Object in ASON is just a map, just a hash map, or no, I think
Hash map.
Hash map, yeah. And we have instances of that, so that's fine. Array is just an array, pretty easy. String is string. Numbers because you know JavaScript or whatever, you know you have to know if you're encoding an integer or a double. Encoding bool is very simple, so I mean that's all there is to it. Similarly, with what we saw with that term module, right? You just peek to see what you're decoding because JSON can be arbitrarily structured, and then you just use the correct decoder. So you can actually just take any arbitrary JSON file. I think I have this demo built. Let's see here. So we will encode something. Let's see, yeah, okay, encode test vectors, I think, yeah. Right, okay. Yes, and then we have there should be a .cbor in there as well, yes. So now we will do demo dump cbor. And then we will do test vectors. Right, and unfortunately I didn't add a pretty printer here, but if you sort of just like piece out any particular thing, right, it's just decoding arbitrary cbor, right? You got the string, you know, whatever the name is, and you got another one, and you know, this is inside some list, which is actually a map, you know. So you can actually, you know, just dump arbitrary ASON, you know, or arbitrary JavaScript into a cbor file, and then just, you know, decode it again if you want. And then we can also decode back into JSON. Right. And the tricky bit here is because there's no ordering in JSON, you know, the output might not be exactly the same. Structurally it's the same, but you know, the fields may be in different orders, you know, just due to, you know, however they come in and go out. So that's really, which, you know, I mean is immaterial, but, you know, and that surprisingly sort of, this arbitrariness to the keys actually makes, you know, JSON kind of hard to parse, right? Because you can't really expect to get anything, right? So ASON actually has sort of similar problems to binary, where it builds like a really big intermediate structure that, you know, causes lots of performance issues, because it has no knowledge of, you know, if it is going to get another field or if it's going to get another object. So it has to like build this background thing, and then as it's parsing, it adds to it and adds to it and adds to it. So you get this big intermediate structure in the background. One of our clients had a problem with something like that. They had a big data set they needed to load into memory, and because binary, you know, just wasn't nearly as size or space efficient, it ended up going into swap. And then ASON also had problems where these intermediate structures were using a lot of data, and so they switched to cbor, and I think they said it was something like over an order of magnitude improvement in startup time, like easily.
A similar thing. I've talked about these succinct data structures for encoding JSON and decoding JSON efficiently and whatnot.
Yeah.
There's actually an implementation of that that's on Hackage now.
Oh, really?
As HW-succinct by John Kai.
Oh, okay.
So just so there's another data point out there for folks who are looking for things in this space.
Yeah, okay. And since speaking of that, so it wouldn't be complete because we're about to be done here in a second. Let me see if I can find that. So I tried to snip Duncan's numbers. Unfortunately, I didn't get time. Wouldn't be complete without actually looking at some of the actual numbers. So here's an example, right? So we have a couple things. We have show, ASON, binary, serial, and the new library. That is encoding something. In fact, it's like it says here, like most libs are actually like not even much faster or even sometimes slower than show, which is kind of embarrassing as hell. But look at how fast we are. That's awesome. And then I think there's actually a oh no. Okay, good. It's cached. Yeah, here we go. So there's some. So like one problem too is that a lot of this stuff isn't going to manifest until you actually get like into bigger data sets. So you know, for here, like with you know small ones, you know they kind of you know sort of all you know look roughly the same. And then whenever you actually have macro benchmarks, it looks a bit different, right? So you got these like sort of micro ones, and you got these sort of macro ones where they're really not even, you know, sort of, you even look here, you know, it's like it requires tuning here, but in practice it actually just, it doesn't even matter, you know what I mean? Because you're not doing it on a big data set. One example is the hackage index is serialized with binary, and I think it's like half the size, like less than half the size in CBOR. And I think there's a size thing in here somewhere. There's also, I think there's a size for the output and an object size one. Oh yes, and here's some allocation numbers, right? So this is the garbage collector time versus the mutator. Mutator is blue, that's your program. That's a major cost, obviously, if you just look at that. And then whenever you allocate a lot of garbage during, you also allocate a lot of garbage during deserialization as well. And then if you actually, that was the previous one, so note there. And then if you don't like accumulate stuff in memory, that's what the mutator versus actual garbage collector time goes to. And then here's actually the new version, right? Here's binary, here's the total allocation it does in the max residency. Here's serial. Here's our implementation, right? You might notice that the max residency is about the same, which kind of makes sense, right? Like if you're parsing, you know, a blob of data, at the end of the day, once it's in your program, it's probably going to be about the same size, you know, roughly speaking. But the allocations are massively different, like an order of magnitude, almost an order of magnitude difference here, which is huge. So you don't really get much better residency, which maybe is to be expected, but.
What's the difference between const and stack?
This is sort of some that sort of a detail. That's why I wanted to snip these out. It's an implementation detail that we sort of abused to see if we could get a lower max residency, and it didn't really help the residency, but it did help the allocation rate a bit. And it's sort of a trick to make. It's a very. I didn't want to go into this because it'd be way too deep. Duncan did it better. It's got to do with the way GHC allocates values. And then we are sort of exploiting that to have like our own stack that we don't allocate on as much. It's sort of this really bizarre arcane trick that has to do with the way closures are allocated. The spineless tagless G machine. And yeah, then there's some other ones. You know, right? So there's like the mutator and GC time. You know, roughly kind of the same. And then yes, here's the object code size, much smaller. Much smaller, over half, less than half the size. So that's actually quite a nice bonus as well. Because you know Haskell binaries are pretty big, which is a bit unfortunate. So that's actually a pretty nice bonus. Yeah, and I think we're about to wrap up here and be in the next slot in 5 minutes. So did I go too fast? Did anyone understand it all? Okay, that's you know more than last time hopefully. Yeah, so if you want to use this library, you can find it here. Where is it? So it's on GitHub under the well-typed account. And then I have a list of issues. If you know, even if you're sort of new, if you want to help on this library, I would really appreciate it. And a lot of things are actually pretty simple. Some things I would just like it if people tried to use it and just gave some complaints and feedback on the API. There's some fun ones here. Like for an encoding, right? Remember, because an encoding is a syntax tree, it should be very possible to write like an awesome, like, you know, really pretty printer for that, right? So you could pretty print, you know, some kind of map like that. Or you could even print it out to JSON. Lots of little like fun things you can do here. And as I said, why not both? You know, some of them are sort of more open problems. Reviving benchmarks, increasing code coverage, stuff like that. There's actually quite a bit of stuff here that would be, if you know anyone's interested, you know, let me know. I'd be more than willing to help guide through a lot of these things. And a lot of them are, you know, just, there's even some byte shedding tags in there. So, you know, if you just want to get your byte shed on, do that too.
Is there an issue for the serialized with the...
No, there should be. Damn it, I'd have to use, I'm gonna have to open my phone, two-factor auth. Yeah, I'll file it, don't worry.
So you said that the hackage index is smaller in CBOR. Do you mean the actual serialized stuff is smaller, or the code? Obviously
the code, like the code itself for the two different paths is like basically like, I mean, it's kind of immaterial, you know, it's just like, because you have instances for most of those things already, so I mean, it's not really that big a deal in terms of writing it, but in terms of actual size of the output index, it's about half the size. Yeah, it's actually pretty nice.
CBOR wins really, really well on small numbers.
Yeah. Yeah, like small numbers are a very, very good example.
lot of
where-
small numbers.
Yeah, like if you have if you're serializing 1,000 ones, yeah, it'll be pretty ridiculously substantial. Which, yeah, is, again, sort of one of the nice things about having a predefined structure here. So.
Right.
But yeah, so other than that, if you want to get involved, I would very much appreciate. You can, pester me as much as you want, and I will, explain everything you need. And hopefully, I had hoped to try and actually get. Sorry, go ahead. Oh, I was just going to say, I'd hope to actually get it released in time to make a release here. I think I tweeted something to this effect, like a cryptographic notarization, but I didn't get to do it. So, so your help would be appreciated. I want you. So I think that's it. Thank you. Oh, I'm sorry.
So you did performance comparison with binary. Is there a sort of reference C++ implementation?
For CBOR? Yeah, there is a lib-cbor out there. I think it's the canonical implementation written by the authors. So.
And how is your performance relative?
We actually haven't tested that yet. I don't actually even know if it's gone through a particular optimization or anything. I think it was mainly meant as like, this is a canonical library to reference, but that would be an interesting thing to benchmark. And it's interesting to think about techniques like this in other languages, right? Like this technique may actually translate pretty well into other domains.
This is not FFI'd at all? There's
No, this is all 100% pure Haskell.
That also creates a problem with like any sort of attempt to try and benchmark off of the C implementation because C is not really known for its ADT support.
Yeah. I mean, yeah, you would essentially have to end up like, you wouldn't really serialize ADTs, you'd be serializing like values and comparing them. Yeah, so. But okay, I think that's it.
It's not really known for its lists.
Uh-oh, I didn't unplug the thing.